Okay, welcome to the hottest seminar. Today we are pleased to have Greg Langmead, who will be talking about discrete differential geometry in homotopy type theory. Please go ahead.
Thank you, Dan. Hello, everybody. It's a real pleasure to be here. Um, I would say I might even be starstruck to be here, um, but maybe we'll confront that. Might be some imposter syndrome. Confront that together here. This is work I did for my long-running master's thesis at CMU here with Steve Awady, and with a big shout out to Mathieu Anel, who helped me really codify some of the intuition that seemed to be going somewhere, but took some work to make it truly rigorous. So differential geometry in homotopy type theory has been a goal of mine for a long time. Once I learned about this thing called discrete differential geometry, which we'll meet along the way, things started to click. So the point here of what we're trying to do is to bring some constructions into hot, sort of port them that deserve to be called geometry. Namely, today, connections and curvature of a connection and vector fields, those constructions. And the index of a vector field, we'll see that. And then a theorem in dimension 2, classical theorem that will prove here that the total curvature on a manifold, or our object of that, is equal to the total index. And the classical context of a vector field, total index of a vector field. The classical context is the following. So classically, we would say if M is a compact, smooth, oriented, two-dimensional manifold without boundary, we can put two different constructions on it. One would be a connection on the tangent bundle, and the curvature of that connection is called FA. On the other hand, we can put a vector field on the manifold called X, and it'll have some zeros where it vanishes. And the theorems are, or you can package two theorems together into this one. You guys can see my cursor, correct? Good, thank you. That the total curvature divided by 2 pi is equal to the Euler characteristic. That formula is called the Gauss-Bonnet theorem. And that the total index, the sum of the indexes at all these vanishing points, is also the Euler characteristic, and that's the Poincaré-Hopf theorem. And what we're going to do today is create our analogs in hot of these two left-hand expressions and prove that they're equal. And we won't have, for now, our own Euler characteristic thing hanging around to prove that they're equal to. So we'll satisfy ourselves with this equality here. So as a reminder of some of these definitions real quick, classically, the index of a zero of a vector field, there are three possibilities, 0, 1, and -1. And there is such a thing as an index 2, 3, -2, 0 point, but the vector field can always be perturbed to separate into distinct zeros that are in one of these cases. And what these look like is the hand-wavy classical way of saying what the index is to like take that left-hand example, follow a red arrow and watch how it rotates as you move around the zero. So this red arrow in the left-hand picture is at 1 o'clock the whole time you move around the zero. It doesn't wind around the circle. So that's an index 0. So it's a winding number. The next example, you start at the top of this, above the zero, pointing at 12 o'clock, and then that red arrow turns all the way around as you move around the zero. So that's a winding number of +1. So that's index +1. And these next three are also all index +1, even though when I look at them, I always have to remember because some of them look like they should be negative, but they're all +1. They just start at different clock positions at the top. So 6, 9, 3, and they wind once clockwise around in all cases till you get to the last one. And that's how you do index -1 is you turn counterclockwise once as you move clockwise around the zero. So that's what's being summed in the Poincaré-Hopf theorem is indexes, winding numbers like this. Now, when we did this, when we waved our hands, we were implicitly using a connection because we were comparing the red arrow along all different points around the zero. And that's the exact kind of classical way of doing things that we can hopefully improve on in hot and rigorize a little bit and see what we're really doing. So there's kind of an ad hoc connection comparing vectors in different fibers, maybe a trivial one in a tiny patch near that zero. And we'll come back to that. So that's what the index is. You can compute the Euler characteristic then by Like on the sphere, you can take this eastward vector field, or on the right, this south pointing vector field. And we get, in both cases, at the north and south pole, one of our examples of a +1 index. So these vector fields are counting the Euler characteristic of 2 that we expect. And then the other theorem that's connected to this is the Gauss-Bonnet theorem. So that's about the total curvature divided by 2 pi. So in 2 dimensions, curvature is a real valued function at every point. It can be positive or negative or 0. And this total curvature integral is just going to sum that at every point, integral style. Maybe there's like a dA volume element there if you want to be complete to show what you're integrating. But like on the torus, which has Euler characteristic 0, the curvature in this embedding of the donut is negative sometimes and positive at other times. And when you integrate it all up, they all cancel out and you get a 0. So that's hand wavy what the Gauss-Bonnet theorem is doing or saying. On the right, you have a sphere, which let's say has constant curvature 1, and this integral is then just computing the total area of the sphere, which is 4 pi, and you're supposed to divide by 2 pi, and there you get your 2. So those are the classical results we're going to take a look at. And the plan will be then to define our own class of manifolds. They'll be combinatorial objects, which we will turn into hits, into higher inductive types with pushouts. And then we will put principal bundles on them, which means families of torsors. And we'll observe right then that we already have the connections and the curvature that we want hanging around. And then we'll put the vector fields on there, and then we will prove that theorem. The background for this talk would be torsors, higher groups. So these first 2 papers cover that very, very well. So we'll make use of that background here. And then the final paper there, the Skokola paper, has a point of view that we'll reference. I'll tell you when we're talking about it, about if you want to construct a map like the kind we want into an Eilenberg-MacLane space, like the type of circle torsors, then you can think of it as mapping into a connected component of the universe first, and then a property will let you lift that or factor it through the Eilenberg-MacLane space. And that's just how we'll think about how we're going to get the maps we want. So that's another piece of background that's handy. Okay, so the manifolds. There's a bunch of different takes on manifolds. We're going to use classical simplicial complexes, and we're going to turn them into hits with a realization procedure in an intuitive, I think, way. You do the gluing that's being specified by the edges of the complex faces. So in abstract, this is in sets now. Simplicial complex M of dimension n is an ordered list of sets like this, n plus 1 of them. And the 0 set, M0, we call the vertices. And then all the MKs, which we call K faces, are K plus 1 cardinality subsets of the vertices. And they're downward closed. So if you're a face in MK, then all of your subsets are in some appropriate MJ below that. One thing you can do is you can take the ordered list of sets and stop at K instead of N, and that's called the K skeleton. So an example in the upper right there is this is a Hassa diagram, which I learned all about in the Agda Unimath library of Egbert and Company, where they have a library inside there all about polytopes. And this diagram is expressing the 3 levels of faces. So at the bottom, you have your, in this case, 6 vertices. This is the octahedron that you see below. And then you have a row of pairs and then a row of triples of faces. And the lines connecting everything up are just telling you the post-set relationship of containment between these sets. And you don't really need them here because we have named every single element, so you can tell which ones are contained. But the diagram in general has these lines. So again, abstract, right? These are just discrete points. You can perform a geometric realization classically and get a picture like the blue octahedron down here. And by the way, these names, these letters I chose are because of the colors of the dual object, the Rubik's Cube. where it's white on top and yellow on the bottom, and blue, red, green, orange going around the equator. So that's what one of these is classically. Another example besides the octahedron would be the complete simplex, which is like a ball, delta of n, and it's n plus 1 vertices and the power set, every single subset. So like delta of 1 has 2 points in it, and so it's this contractible interval. Visually, the boundary of that, so the boundary of such a thing is our nickname for the n minus 1 skeleton. So it will lack that last filler set that has all the vertices in it. So for this interval, its boundary is this zero sphere. These will be our spheres. And delta of 2, which is this contractible filled-in triangle, its boundary, n minus 1 skeleton, will be a triangle. And that'll be one of our various circles. We'll have a few different circles in this talk. Okay, so now we're going to do a realization, a homotopy realization. So we'll do a sequence of pushouts. I suspect what's happening here, and I don't need to know this, but someone who wants to think about the shape modality, it's probably what we're doing. We're taking the shape of this complex and bringing it into a higher type. But regardless, so the base case, we're going to go up to dimension 2 one at a time. We'll stop at 2, but it's fully general. The realization we'll denote with blackboard bold M of a zero-dimensional complex M is just that set, just the set of vertices. So in particular, the zero sphere, which we can add a blackboard bold to show that it's the realization of this thingy, is just that zero sphere of 2 points. So we're going to kind of bank the sphere in this dimension and use it when we define the next dimension. And we'll do that one more time. So in dimension 1, right, a complex would be 2 sets, vertices and pairs. And the realization we have in mind is this push out. So the vertical map on the left is this set of abstract edges, each one equipped with a zero sphere. And this vertical map down is just recapitulating the combinatorics of which 2 vertices that edge, was or is connecting, quote unquote. And then the vertical map on the right is just an inclusion of a hub point for each of these edges, and the push out, the filler, will glue that hub point to both those vertices. So that's how we're expressing that we sort of do the gluing that the edges is telling us. So now we have an honest, at the bottom right here, this push out 1 type. So we can do this in particular to our triangle, which will get us ready to do the next push out. And you can, like this diagram in the bottom right is just that data of its 3 edges, which are, have names with these elements that tell you totally specify which 2 you're going to glue them to. And this filler will glue these 3 hub points to those vertices to make the triangle. So it's bold, blackboard bold, because now it's a 1 type. And here's the octahedron's 1 skeleton. So we'll call the octahedron's realization as a type bold O. And so it's 1 skeleton bold O1 would be this. Here's those vertices, 6 of them. There's 12 edges up here. And you glue them all together like that. So to go to dimension 2, we'll make use of both our spheres that we did, the 0 sphere and the 1 sphere. So here's that push out again that builds M1 by pushing out the vertices with the edges. And now down here, we will take the face data. So we have 3 sets now. M2 is triples or faces, each equipped with a triangle that's one of our 1 types. And we'll map that into M1. And then this vertical map on the far right going up is the hubs for each face, which will then be glued to the entire triangle that they belong to. So hub and spoke style, like in the hot book. And we have now running along the middle here, this sequence, which is our analog of the skeleton maps, M0 to M1 to M2. So here's the full octahedron. We had this push out already, and we add this data here of the faces such as the white, green, red face, and it gets glued together. Now we have these hub points hanging around. We're not going to use them. They're there in this formal construction, but we're just going to look at our vertices, edges, faces, and kind of skip the hubs. Maybe they have some use going forward. There were moments where I thought I needed them for something, but not yet. And so here's for the octahedron, this map, again, along the middle of his skeleton, mapping to each other. Cool. All right. So one last thing about simplicial complexes, this is all classical, this slide, is the link. The link of a vertex is the faces that don't contain it but are nearby. Their union with that vertex is a face. So in the octahedron, the white vertex has link this equator here. In fact, all the vertices have some analogous equator that is their link. So like the blue-red edge here is a face whose union with W is this face. And a combinatorial n-manifold, again, this is a classical definition, is a simplicial complex, all of whose links are simplicial n-1 spheres, some fixed dimension sphere. And by R, I mean the geometric realization of that link is homeomorphic to the n-1 sphere. So these are a model of a tangent space in a way. It's the next nearest points, and there's a sphere of them. So what are we capturing with such a thing? Like, what manifolds are approximatable or triangulable to such a combinatorial manifold? One of the theorems, and there's a zoo of theorems that tell you all about what's smoothable, triangulable, PL structure. Here's the one that makes this most relevant for me, is that every smooth n manifold in all dimensions has a compatible structure of a combinatorial manifold. When it recapitulates what we just said, it's n-1 sphere, link at every vertex. You can read more about that at this NLAB page. So every smooth manifold can be triangulated into one of these. So if we work with these in hot, then we're working with a proxy of a useful class of manifolds that they're related to. A counterexample, like a non-combinatorial manifold, would be maybe something like this. This is a simplicial complex, but you see that its links are not, they're both not constant dimension, and some of them aren't even spheres, I think, because of the way this is stuck together. So a combinatorial manifold is like a smooth manifold with circles, like a two-dimensional one would be always have some kind of polygon of neighbors of dimension 1 always on a 2 manifold. Okay, so torsors. We want principal bundles over these things, these simplicial complexes. So we want families of torsors. That's what a principal bundle is. So let's do that. So let's remind ourselves, I'll sort of read into the record here some of the facts, commonly known facts in homotopy type theory about torsors. So G is a group, any group, higher group. A right G object is a type that has an action of the group, so a homomorphism like this. Such a G object is furthermore a G torsor if it's inhabited and if this map that packages a projection with the group action is an equivalence. And this sort of packaged together some of our shorthands that you might be familiar with, such as picking a point of X, for example, in both these left components, then gives you an equivalence between G and X. So X is one choice away from being a copy of G, quote unquote, picking a base point. And since this is an equivalence going to the right, there's an equivalence going back, its inverse, which is a projection and a map we can call subtraction, at least if G is commutative, that's a reasonable word for it, where you take 2 points in X and it tells you the unique element of the group that takes the one to the other. We'll make use of that. So that's what a torsor is. And then the type of all such types that have the structure of a G torsor is called BG. And it has a base point. that isn't meant to be my name. It's the G torsor of G acting on itself on the right. So we'll import a few facts about this. That type BG of torsors is a delooping of G. So the loop space at that base point is G, and the composition of loops here corresponds to multiplication in G, just is a copy of G. And it's connected, and those two together tell us that it is a KG1. So by wanting principal bundles, we've gotten ourselves into this discussion of Eilenberg-MacLane spaces. So that central H spaces paper is a great resource for reminding yourself about all these relationships. And there's a good section in there. I think it's section 5 that's talks about everything they've constructed in the case of torsors, like BG here. So for us, we want to map into the circle torsors, right? That link of each vertex is a square or something like that. For the octahedron, it's a square. It's a circle-like thing. So let's look at this sequence of maps. We've got the universe. We've got what we'll call mere circles. So these are types merely equivalent to the circle, which would use the usual notation of Biot as one for that. And so we have a candidate map into there, the link, and then it's a property of such a map that it factors through BS1. And we'll assume we have, like in this talk, we're not going to sweat it too much, that we'll have such a lift whenever we need it. It's a choice of orientation in 2 dimensions. That's what's the property that your family of mere circles is oriented, tells you that it factors through this map. So that this perspective of we have a map into a component of the universe, and then there's a property that map can have that tells us whether it factors through an Eilenberg-MacLane space, is exactly the point of view explored in that Skokola paper.
So, Greg, just to clarify that you said it's a
Yeah.
property, but it's also a choice of orientation. So I think there is some data in that lift, right?
That's right. That's true. Yeah. A choice is a choice of factorization. And then the mere existence of orientability would be the mere existence of the factorization.
Okay,
Yeah.
good. Just clarify.
Yeah. There's a type of, factorizations, I guess you could say, type of orientations. Yeah. Saying it's a property is because I secretly truncated to say it that way. So other names you might know some of these types by, like Biot S1, the mere circles, you might call BO2, the delooping of O2 acting on the plane. So it's got the rotations and the flip. And then in the Skokola notation, it would be EMZ1, which is his notation for the connected component of the universe of types equivalent to the Eilenberg-MacLane space KZ1. And of course, S1 is KZ1. So EMZ1 is this mere circles. And in the written paper version of this talk, that's what I call it. So that's another name. And then BS1 on the left there is BSO2, just the rotations. And it is KZ2. So we have our manifold, and we're going to map into, sometimes we'll just talk about the mere circles, and sometimes we'll be clear that it's BS1, in fact, that it factors through. But the link will give us that. So let's look. So what I claimed is that we've already, with this setup, got things we can point at and say that's a connection and that's curvature. And the connection is just an extension of a bundle to the next higher skeleton. That's what it is. So let's see it play out. Remember, we have the link. So the link of W in our octahedron is that equator, BRGO. And all the other vertices have a similar looking link. So we will define the tangent bundle on a combinatorial manifold to be the link. It only works so far on vertices. Each vertex goes to its link. So we'll call it T0. And it links, it maps into the space of mere circles, in this case, these squares. So supposedly, what I'm telling you is that if we can extend that to the one skeleton, that would deserve to be called a connection on the tangent bundle, an extension like this, T1. So for us, we've got these pushouts, and we're almost sort of called to keep going, right? We want to define a map out of M or M2, then we have to work constructor by constructor in our hit, and we have to keep defining T on the next constructors, say the edges. So that's our reason for wanting to extend a map to the one skeleton. But classically, just to briefly touch base with their motivation for defining a connection on a bundle is there's a couple different ones. And this is exactly where those sources have always been in my decades of enjoying that material, confusing in a way that maybe we can bring clarity. So, for example, some of the motivations, if you read like John Baez's book on differential geometry from the 90s, they might say, we want a connection because we want to be able to differentiate sections of bundles. And then a few pages later, well, we actually also want to be able to associate points in different fibers, which we can do now that we have a derivative of sections of bundles, because we can take a path and solve a differential equation and give us a mapping from one point to another. And then you can prove a theorem that you can do two first and derive one by differentiating that. But they're adding structure. And it's not always, these motivations aren't that compelling to me, not compared to sort of what we can say, which is, well, we got to keep going. We got to go to the next skeleton. And so therefore, so that's the point of contact. And the point I'm making here is just, if you know this old other classical language, then that's might be why what we're doing here is like that. But I think it might also be the case, just to touch base with what John Sterling was saying last week about using homotopy type theory or using a proof assistant to teach mathematics, that we might have an edge here and make some things clear. Now you can be the judge. That is an aside. So let's keep going with T1. So let us define a map extending link. If we want to extend link, then let's look at like one edge. Let's look at WB and let us define an extension of T to that edge. So it would have to be a isomorphism between the link of W and the link of B. So I've drawn the link of W on the left, and I've made an edge red so we can keep track of any movement or rotation. And we have a choice at this point. There are many ways to extend T0 to T1. I'm going to choose one that I'm calling tipping. So we're going to leverage that we have a pretend picture of this octahedron in the room in 3 space with us, and that we have this particular equator that we can imagine tipping up so that it touches the north. So that gives us visually a map that we would then have to write down all the data. So T1 of G in the link of W goes up to W in the link of B. And B in the link of W goes down to Y. And then R and O in the link of W go to R and O in the link of B. So they kind of stay fixed. You're just spinning this ring. So, and there's nothing special about W and B. There's a complete symmetry here to the octahedron. So we can use this method to define T1 on every edge. Of course, I have to define it on the edges between like G and R, and you do that in the obvious way. This tipping sort of tells you the data. So that's a T1 that we could choose. Let us look at it now on a concatenation of edges, a loop from W to B to R back to W. And we'll denote that loop by boundary of the face WBR. So let's do T1 on that loop. So this is visual. You can use your hand here, and the Rubik's Cube helps too. So you have this link of W, which we tip up. That goes from W to B. To follow the edge from B to R, we're going to tip, and it's going to turn to face us. And as we go from R back up to W, it will fall backwards like this. And so the net of doing all of these moves is that this equator has come back rotated by 90 degrees to the clockwise. And we'll give that rotation at name R. So it's an automorphism of the link of W. This square is tailor-made to detect rotations by exactly 90 degrees in our rigidly drawn picture here. So that's cool. So that captures some kind of curvature maybe. We'll give it its proper name in a minute. What about then extending T1 to faces, to a T2? Well, this face is filled. Let's give a name to the homotopy, the filler here, which is a homotopy from REFL of W to the loop. Let's call that the filler. So if we're going to have T2, then it's going to take in an object like this, of this type. So that would mean that T2 would have to live in this homotopy from T1 of REFL to T1 of the loop. T1 of the loop is R, and T1 of REFL is the identity. So T2 would have to be a homotopy from the identity to R. We can call it HR. So we would need a path. So plugging in a point to this homotopy like G, it would have to be a path from G to O. G to the rotated 90 degrees away vertex O. And we'll choose, so there's again a choice, just the edge GO, the minimal edge. So it's telling us, it's kind of like the little movie that says we turned like this. So this two-dimensional object here, this T2, is recapitulating T1, but as a path from the identity to that end point. So it starts at the identity and ends at the T1 value. And it, just to keep talking about the Rubik's Cube here, you can just see this on the Rubik's Cube. If you put your hand on it, or I draw this with my minimal GeoGebra skills, this little face, it moves to the blue face, comes around to the red face, comes back up to the white face, rotated. And I'm thinking that that rotation that took place, it took place here, because with respect to white, the move from blue to red is the rotation. If you go back to white and check what you just did, something like that, doesn't matter. But that was what this led. So that is differential geometry. It's just been discretized because we do everything in chunks. But that's very much about the curvature of the sphere snapped to a cube. So the formal definition of a connection, and then we'll do curvature, is an extension. So if we have one of our realizations in n dimensions, and here's that sort of spine map, and there's pushouts, that I'm not drawing here, pointing into all these. It's, let's say that we have one of those, and we have a type family on the whole thing, and all these triangles commute. Then we'll name the map FK that stops at the K-skeleton, or that maps out of the K-skeleton. We'll call that a K-bundle, and we'll call the proof that it is an extension of everything to its left a K-connection. So the connection lives in that delta from the one dimension to the next. So where's curvature? So curvature is a piece of that extension. So let's draw M1 and M2 only, and here's the type families and the filler that they're an extension. And then let's remember the pushout data that was up there. A bunch of faces that got glued onto M1 to make M2. So looking at just one face and the outer square of this over on the right, the fact that this is filled, right, which all comes from the fact that we extended T1 to T2, is saying that the type family around this triangular face is contractible to the type family on this one hub point. So it's another statement of flatness or triviality on this face. So that face, that single face statement is what we'll call curvature. So for us, like T1 around a face on the loop, we'll call that the curvature at the face. And then we have a filler that says that it's trivial, or a path to from the identity to that rotation. That filler is called a flatness structure. And this doesn't really have a classical name. But what I want to point out about using the name curvature here is that it's local. So you may also know the word holonomy, which I don't think I'm going to use. Holonomy is also the what T1 would do to a path, some kind of automorphism of going around some loop. And that loop might be global, it might be big and go around donut holes and such. That's holonomy, but curvature is therefore a kind of special case of holonomy that's local. So we're going to restrict it to just one face, curvature. This is true classically too. It's just a local construction. But we get this other piece that was coming from the fact that these faces are all, filled, and that's called the flatness structure. So we'll always have these two things, an operation like a rotation, and then a path from the identity to that. So in this move from the upper to the lower, by the way, I again got rid of my hubs. So up here, there was this hub point that the triangle contracted to. And down here, I'm talking about a vertex around and a loop around the face, because that's my preferred way of thinking about it. But just so I don't overly confuse people, up here is hub language, and then I get rid of it because I don't need it. So this distinction between like a rotation by 90 degrees and a path from the identity to rotation by 90 degrees, I get confused. Mathieu and I would sit around and argue about which one deserves the name angle. I still don't know. So that might be a point of confusion. Okay, so connections, curvature, and then vector fields. So let's do that. A vector field classically is meant to be a section of the tangent bundle. So let's set ourselves up with a tangent bundle on the whole two-dimensional realization of a combinatorial manifold, all the skeleta. And we're going to stick with oriented, so we have the honest BS1, and we're going to stick with 2 dimensions for this definition. And that's all I have in the full paper too. So we're following a thought process here. Classically, a section of the tangent bundle is a vector field. Now, of course, we don't have a vector bundle with zeros in it. We have a circle. We have a non-zero vector bundle, as it were, of unit vectors only. And so if we were to have a section of this, that would be a lift of the map into BS1 to the point, to the ES1. And that would be a trivialization of the bundle, which we do not want to have or claim to have. So it would be a not good idea to say that a vector field is a section of this whole thing, because these are just non-zero. That would be like saying a nowhere vanishing vector field, and that is not a vector field in general. So what will we do? What would be the analog of a vector field in general that might have zeros? And our solution is to say that a vector field is a section on the one skeleton only. So this we can always have on a 2-manifold. So we're modeling a non-vanishing vector field on the one skeleton, and we're modeling the vanishing of a vector field like this one. So you can grab your octahedron and turn it in space in the room, and it'll permute the edges like this. And so that's something we would like to consider to be a vector field for us. And it will, if you were to think of it classically as a sphere that you did that to, you'd have a zero inside this face somewhere and inside this face somewhere. So we're modeling the vanishing of vector fields by omitting the faces. All the faces are omitted. Might be that the vector field does extend to some of the faces and not others, but we're going to say it's just a section on the one skeleton. And this will be an example that we'll work through. Okie doke. So where we have sections, we have pathovers. So let's remind ourselves real quick about pathovers, also called dependent paths or path over with a space between the words. There's an asymmetry in their definition. So if you have like a type M and 2 points A and B and a path between them and a type family over that with alpha in the fiber over A and beta over B, then the type of paths over P is the type of paths like this pi path that go from the transport of alpha over here to the native point beta that we started in that fiber with. So you got to pick a fiber, go over there, and look at paths there. That's the type of path overs. Now, when you have a section, a dependent function like our x, it chooses a path over. It's got an action on paths, a dependent action on paths. And so it will map this p to a particular pi. And so that the notation like from the hot book would be APD of your section on the path is a particular term of the type here. This is the type of path overs, and APD picks one. So you transport the XA over, and it'd be equal to the native X. You can also just call that X of P functorial style. So we're going to have that. So we're going to do computations with that. We want to define the index of a vector field. We want to get at our theorem. So we want the index of a vector field on a face, and we're going to do that by taking X of a loop around the face. Like X of the loop in that functorial style. So a path, a loop over this loop around the face. So let's do a computation with an example. So we've got a face and its boundary here. Face is missing. And we've got V1, 2, and 3. And we've got the three tangent spaces, which in the octahedron are squares. So I'll draw them schematically like this. And then let's start looking at the data of X of this whole loop. So X, our example X, I've made a choice here. Let's say that X at V1, and we'll nickname that X1 for short, is this thick black arrow. Now, to compute X of the whole loop, we have to take all the data of what X is doing on all these vertices and edges and transport all of it to one place. So we're going to pick T1, and this vector X1 has to be transported all the way around the loop, and other data also has to go around all or part of this loop. So let's start drawing it. So let us suppose in my example that transport from vertex 1 to 2, and we'll call that fiber isomorphism T21, because it takes in things from T1 on the right and it spits out things in T2. So that's the map that goes. And let us suppose that what that does on the sort of piece of paper here is trivial, just slides up from this vertex to this one. So this vector gets mapped here, and I've thinned it out to show that it came from somewhere else. Let us further suppose that T32 that transports to the V3 rotates by 90 degrees clockwise. So that's what happens to the same vector, and it's been transported twice now, so I'll draw it dashed, and then let us suppose that T13 along this edge is trivial on the page again, and so this dotted slides over, dash slides over, becomes dotted. So that's another piece of data we're going to need to collect to do X of the whole loop. The starting vector, and it gets transported. So what about the rest of the data? So here's the rest of the data. So for example, up in vertex 2, there's a native X, X2. Let's say it's here. I'm trying to make a maximally swirly vector field with this very discrete set of points. To draw a path over, the path over this red path needs to connect the transported X to the native X. It's important that it starts at the transported point, goes to the point X of that point. So this red edge will perhaps become this path over. It has to connect this arrow and this arrow. When we then take these three elements of data, two black and a red, down here to the V3, it gets rotated by 90 degrees to the right. So here it is thinned out, and there's the red edge. And now there's a new native vector, X3, and we need to draw a cyan edge from X of V2 transported to X3. And then all of this data drawing moves back to T1 trivially, sliding, and the arrows fade out. And we get all told that this triangle comes in. We translated all of it to the T1 to this three-edged thing inside of a square. So there's 4 points and 3 edges here. And I can't help but think that we scooped some ice cream, we dragged an ice cream scoop along these 3 colored edges, and now we have like a scoop vertical and my tangent scoop ready to go. So we're going to call this path here, this X of the loop. in our chosen fiber, the swirling of X at this face. So it's almost the index, not there yet. It is swirling, though. We can see movement because X spun, even though the tangent, right, T32 rotated by 90 degrees. Some of our curvature was happening at the same time, but X was doing some of this. So they're coupled together. So we're going to work in a second towards uncoupling them. Here's symbolically what we did with our fibers. And then in the final fiber, we built up 4 points and 3 paths connecting them with these names. So an inventory of what we did. At a face, we've got curvature, which is an isomorphism of one of the tangents. We've got flatness, which is a path from the identity to the above curvature. And we've got swirling, which is a path over. So it goes from a transport of x1 around the loop back to x1 itself. And there's a symmetry we can see here that flatness, if we were to plug x1 into flatness to ask what it does to that particular tangent vector, we would see a path in the opposite direction from this path. So we're going to make use of that, and we'll call that the flattened swirling. So the flattened swirling is flatness on x1, which is now a path from x1 to its transport, padded with the swirling, which goes back the other way. This is now a loop from x1 to itself. So here it is in our square we had a second ago, a new orangish, brownish arrow that goes from x1 to the transport. And it will allow us to complete, in this example, a loop. So the index will be the winding number of this thing. So remember, though, that the integers are only the loop space of the honest S1. So we're going to have to map this fiber, this square, to the honest S1 and compute the index over there. And that's fine. But if you're like me, then you might be happy to think about the winding number being clearly visible as a 1 right here. And that's fine too. And by the way, what does it take to have an isomorphism between this square and S1? It just takes the choice of a point. And X itself has provided that. Here's the point. So this will go to base in S1 and this will loop around. So there's our index in this very constructed example. And there's part of our answer to the question at the beginning. So the index of those red arrow things I drew, you hand wave classically and say, go around the loop, maybe create a chart and a trivial connection to allow you to compare these vectors to each other. Well, we don't get to do that because we have the type family that we have. And as we moved around a triangle on this extremely curved octahedron, we were forced for the curvature to be there. It wasn't a trivial chart or a trivial connection, but we do have the flatness structure that tells us exactly how to subtract it back out if we want to. And then we get something like the classical, if there was no curvature, loop winding number. So we're ready. So we've got all the ingredients, and we now need to total things. Those theorems, Gauss-Bonnet, Poincaré-Hopf, are about total index, total curvature. So total swirling, I consider that big red, cyan, and blue triangle kind of a mess. We had to transport a whole lot of data to a given fixed fiber to do anything with path overs. But luckily, because we have some extra structure, we can get rid of that dependency. So we're no longer have to do a dependent path, but something much simpler. And let us go over how that works. So here's that four-pointed, three-edged thing that was like the triangle inside of a square. And let us define a new map called alpha I. And we'll use this to move everything that we've done into S1. So alpha I is the map subtraction that I mentioned. When you have a torsor, it's just the isomorphism between the circle-like thing, the mirror circle, and the actual circle. And since we have X, which is a pointing of this square, that's each fiber now has its own private isomorphism with S1. So X, which of course is swirling and doing crazy stuff, but X, there's an X in each fiber. That's an isomorphism with S1. So we've trivialized the bundle on the zero skeleton, quote unquote. So we'll use these alpha I. So we're going to move into S1 now, our transport maps, and then our pathovers. And we'll do some math over in S1. So to look at transport and what it does in S1, we want to do alpha j of tji of xi. So the base point in ti, map it to tj, and then to S1. So here's the diagram of that. So you've got this map between two fibers. They each have their own private alpha I, alpha j. And the question is, moving from this fiber to this, what does it do to the S1 to make this, if we're going to make this diagram commute, what's happening in S1? And it's just some angle of rotation, and we're calling it rho ji. So rho ji is a group element in S1 such that this commutes. And there's maps up, by the way. You can take the base point in S1, map it to xi, and then the loop in S1 will go all the way around the square. So the lemma is that rho ij, rho ji are opposite angles, opposite elements of S1. That's easy to see in the diagram, right? Because, of course, tji is the inverse map of tij over the backwards moving of that edge. And therefore, what's happening down here is opposite for these diagrams to commute. Here it is written out algebraically. And it's the key step here, it's worth just looking at briefly, that what is the sum of these two angles? Let us add xj to it. And I can take these last two terms, and by definition, that's the transport of xi to fiber j. But then I can move this angle inside because it's a torsor map. This tji is respecting the group action, right? So this torsor structure is why all of this is working. And once you move that inside, you've got a copy of tij xj. And then we use the fact that these are inverses. That may or may not help. There's a lemma on the next slide too, like this. Just confusing enough to be irritating. And I'm trying not to import the irritation here, but for full disclosure, that's what that looks like. So we've now pushed transport maps. They're just rotations. They're just torsor maps that respect, that respect the group action. So let's do the same with the pathovers. So here in the parentheses, a pathover. And let's remember that that pathover is a path like this from a transported xi to xj. And we're going to apply alpha j to that path, and we get a path. Where will that path go? It'll go from alpha j of this to alpha j of this. Well, we just said alpha j of this transport is this angle, and alpha j of xj, by definition, is the base point in S1. So all of these pathovers of one edge will go to some angle to base, some path from an angle to base. So we've got these little pathlets in S1 that start who knows where, and they all end in base for each edge. Such things, some angle equals base in S1, these can be directly added using the addition of S1. We'll call it plus prime. And if you have a little pathlet from A to base and another one from B to base, you can add them with plus prime and get something from A plus B to base. And it's like a whiskering thing where if you want to add P and Q, then you take P that goes from A to base and add B, the fixed element B, to that, which becomes a path from A plus B to B. P plus B, A plus B to B. And then Q goes from B to base. So you concatenate them. So that's what's happening. Kind of an unusual, at least for me, thing to think about, but it's intuitive. And what it's doing, this idea of adding B, it's totally like that dependent path business of getting them in the same fiber. It's lining up two elements so they can be added, or concatenated, sorry. So a lemma here is that these are also inverses. So these two paths under this plus prime operation, these two pathlets, they, first of all, it may not be obvious that when you add them together, you get a loop. But in fact, you do. It goes from base to base because the rho ji and rho ij cancel. So one of these goes from rho ji to base. One of them goes from rho ij to base. And the sum goes from the sum of the rows to base. And the sum of the rows is base. So it's a loop, and in fact, it's Ruffle. And this is just a recapitulation that dependent action on paths of Ruffle is Ruffle. Right? So APD in book hot notation of Ruffle is Ruffle. That's how the path induction gets started. And if you write out what that's saying, it's that if you go across an edge and straight back again, then the two paths you get cat to Ruffle. If you want to go across an edge and back, you have to take the journey out and transport it back to compare. And that's just adding two sigmas together so that they line up, right? Adding two sigmas is to make sure they line up and cat them. And this is already lined up and catable. And you get Ruffle from path induction, so these add to Ruffle. And again, there's the irritation. This is maximum complexity, as far as I'm concerned, for this talk, is this little equation. But I think it's just intuitively obvious and frustrating to prove. Maybe I'm wrong. But so we're going to use that in a second. This picture may or may not help, but this is what I was saying, is that APD of Ruffle is Ruffle. So if you imagine going to P and transporting what you got back, that would be the downward arrow here, versus the path over P inverse, which is the upward arrow here, and they cat to Ruffle. And that's what this sigmas is doing with this special plus prime math. So we've taken this, the vector field is why we have all these trivializations and isomorphisms with a circle, and we can do all our math in the circle, in a single circle. So the last assumption that we made that we can cash in now is there's no boundary. So suppose we enumerate all the faces and designate a vertex for each, so that going around each face now has a designated triangular loop that starts and ends at VI. Those are all the triangular boundaries. Then what we call the total swirling is the sum of, in S1 now, of pathlets around every loop. So this is the S1 version of what we did with a big three-color triangle. Go around the whole loop and do that for all the faces. This sum can be reorganized because the circle is commutative, and we're assuming that every edge is traversed once in each direction. That's what the no boundary amounts to. So we can reorganize every time each edge is traversed, it's traversed the other way later in the sum, bring them together, cancel them out. So this total swirling completely cancels, and right, S1 is commutative, so we reorganized, cancellation. All of this that I just said, this swirling and cancellation, this is all, I'll come back to this in a sec, the classical proof. You can read about this in old proofs of the Poincaré-Hopf theorem. All right, so here's our total inventory. We've got the curvature on a face, flatness at a face, swirling at a face, and the flattened swirling at one face, and we just learned how to add everything up. We can total them all in S1. So in our lingo, the total of the curvature of a face is the sum of all of the angles of rotation, and that is base. These all pairwise cancel, so there's nothing to that. The total curvature is base, but the total flatness is something. They were all, remember, they were all paths from identity to the rotation. So that means this is a loop. If the end point of the total flatness is the starting point, this is a integer. So sometimes when you prove the Gauss-Bonnet theorem, you stop and are awestruck by the fact that the total curvature happens to be an integer. So that would be, maybe we could stop and notice that right here, that this is a loop. I've not taken the loop space, I've not done loop of this. This is some kind of path in a circle. All right, we got the swirling. We just said that this total swirling, the sum of all the sigmas is Ruffle, and the flattened swirling was always the concatenation of flatness with swirling. So the total is the sum, and this is just these two items added together. And all of the swirling cancels, and we're left just with another copy of the total flatness. And that's the theorem. It's saying that this total flatness of the curvature is this total flattened swirling of the vector field. This is supposed to be our index, and this is supposed to be our total, whatever, curvature of the manifold. So that's an R-Lingo. And if we take the loop of both these, we get the two integers. So for example, on our octahedron, where we showed that if you go up and turn and fall backwards as you go around a triangle, you get rotation by 1/4 turn. You've got 8 faces. And so there's a 2 coming from the total flatness structure. And then the triangle of 3 colors that we drew was this one with this swirling vector field. And there's another copy of it in the back here. Each of those had a winding number of 1, and that's the other 2 that you'll get. And you'll get no contribution from the other faces. And it's really annoying to write it all down, but it calculates out. So then it's just a punchline. Here's a page, here's a diagram from a recent book that covers Hopf's original proof of the agreement of Gauss-Bonnet and Poincaré-Hopf. And it totally has this discrete flavor. It says, okay, first of all, triangulate the manifold so that all the zeros of the vector fields are in the interior of the faces. And then you draw this diagram like this. And when it looked at comparing along one edge, so Hopf's insight was to come up with a function on an edge, whereas most of the time you need a whole loop to have something you can have an item in one loop, like a group element or something. He figured out that if you can actually come up with a function he called capital phi on one edge, which we called that little sigmas. And it was comparing what the vector field did along that edge to just transport along that edge. And that totally looked like a path over to me. And we just, you just crank through it in hot, and you're really recapitulating, a very discrete flavored classical argument. And a lot of differential geometry has this, where it becomes discrete for a minute to prove something and comes back. So all those infinitesimals, we don't have them in this story, but we still can get at those homotopical properties like Euler characteristic. That's it. Thank you.
Great. We will have traditional silent applause. And then open the floor for questions. Oh.
I could ask a question. Actually, I have a couple. So the realization procedure you defined for simplicial complexes, presumably you can do that for any fixed external natural number, but you can't do it for all internal n. Because I think that would be just the standard coherence problem, right?
Yeah, I suppose an infinite construction would be out of bounds. Yeah.
Yeah. Okay. Which is fine. You're handling two-dimensional manifold, so it's perfectly suited for what you're doing. Just wanted to make sure. I guess I also have a question or comment. It's more just about terminology. So you said that you describe a bundle to be something defined on the vertices only, and you regard the further extensions to higher skeleta as things like a connection and so on. But that's an odd way to phrase it, right? I mean, if we had a sphere bundle on some type, it should be defined on the entire type. And in fact, otherwise all sphere bundles would be equal on a given simplicial complex. Merely equal, I mean.
I doubled back on that definition here. Like this is the real definition that a K, so a bundle on the whole sphere, a two-dimensional sphere, would be a two bundle in the terminology I'm using here.
Yeah. Okay. Yeah. So it's just sort of a terminological complaint about what you said earlier about what a bundle is.
I did. Yeah. I said that let's call T0 the tangent bundle on the octahedron for a minute.
Yeah.
Yeah. Like a zero bundle. Yeah. I should say.
So I guess somehow what you're using is that anytime you have a bundle in hot, we have parallel transport. So all our bundles somehow have connections in some sense,
Yes.
is essentially what you're using.
Yeah. Yeah. And to get at it, like when we have a type and we have a map, we already have the connection. And so if you want to talk about different connections or let me put a connection on, you have to then inductively go up by dimension so that there's this moment where you haven't yet defined on one particular skeleton dimension. And then you can pause there and talk about different connections or choices that you have. But if you've
Yep.
already got, and Mathieu and I would argue about this for hours, he's like, you already have the connection, it's done, you have a full map. And so we would have to stop, before you have the full map to see it. Yeah.
Yeah, that's great. That's very, very interesting. Okay, thanks very much.
Welcome.
I'll have a more naive question. So, when I just saw the kind of title and abstract for this talk and, saw something about geometry, I was expecting this to be in modal hot rather than in, book hot. Is the explanation for why you're, sort of able to do some geometry without any additional structures, the fact that this is kind of combinatorial and discrete at its essence? Or do you have another perspective on that?
Right. So certainly the infinitesimal cohesion and all of that story where there is smoothness and you have a modality to kill it off or whatever. I don't need any of that, but I think we are using the real cohesion shape here implicitly, and I'm just not proving that that's what's happening because I do think it's there because we had a simplicial complex that was a set, and then we actually took those edges and paths to higher edges and faces and so on, and passed into higher dimensional things. And I think that is shape. So I think it's there. We just have our own pushouts, our custom pushouts, but they are doing something like what shape is doing. That's how I'm thinking
Looks
about
like
it anyway.
Steve has either a question or comment. I'll let.
Let's see if I
Yeah.
can get this to work. Is this working? Can you hear me?
Yes, we see and hear you in your car.
Oh, okay. Yeah. Sorry, I had to go somewhere. Greg, can you say something, please, about the formalization or the possibility of formalization or how much has been or could be done? And I'll
Sure.
sign off.
Yep. Okay.
Thanks.
Yeah, I learned a lot by starting to do it. So I did define, all the polygons. So I definitely needed a square and a triangle and so on, and I proofs that they're equal to the circle. That's already written out in the hot book and probably is in all the libraries, like the one that proves that the suspension of S0 is equivalent to S1, where you have 2 points on the circle versus 1, and did all that. And then I was going to prove that the octahedron that I have here is equivalent to the 2-sphere and did not complete that, and I bailed because I was running out of time. And so that would be something worth doing. I guess it would look like, pick a vertex and then the map to the sphere would take one triangle. It would map all the vertices to the one base of the 2-sphere, and then it would map, one of the faces to wrap around, and the map back would pick a vertex and somehow map around the whole thing. I don't know. It was going to be hard, but that is a headcanon, a true fact that I didn't. So you could do that. And then during my presentation of the thesis, Owen was there. So Owen here, maybe you could repeat. I don't think so. Owen
Hello.
Milner was
Yep.
there and asked. Oh, good. Yeah, he asked a question about the link about formalizing the notion of a combinatorial manifold, and that the link are spheres of the appropriate dimension, and that would get you going with something to have a type of manifolds. So where it stands is it's not done, and I just had some ideas about what should be done there. You could take that Egbert's group, their polytopes library, maybe, and apply this push out construction to all of those and get a bunch of spheres and prove they're all equivalent. That should be true.
Can you hear me?
Yes, hear you now.
If someone wanted to do so, I think what I understand is you're not planning on doing that formalization. Is that right? And then if you're not, then it's an open project for someone else who might be interested in doing it. Where would they start? I guess they would write to you, but apart from that, do you have a beginning of it on GitHub somewhere, or do you have a reference in your at the end of your slides or something like that, if somebody wanted to pursue that further?
Yeah, I'll make sure when I send the slides to Emily that I include a link to the repo where, the LaTeX files and all are. And I think I'll make sure I'll check first and I'll push it if it's not there. But the business I just described with all the polygons being equal, and maybe the beginning of what I did with the octahedron and the sphere is somewhere in there. And so that could be a starting point. Yeah. And I don't have plans to keep going with that. So someone could totally do that. I came also pre-equipped with my own question. Maybe it'll prompt some other questions, but stop me if you have one of your own questions at the end here. Apologize. One of the concerns that I have, that you might have, is the fact that the octahedron is so highly symmetrical that we might have accidentally made too many grandiose claims about what was going on. So first of all, the octahedron, all of its links are squares. They all have the same number of vertices. And those tipping rotations happened to be 90-degree rotations that were perfect for snapping one vertex along a square. Neither of those are going to be true in general of a triangulation, even of a two-dimensional surface where you'll have something like this on the right, where they vary here. I think they go from 5 to 7 edges of each link. So there's some pentagons and there's some 7. The average will be 6, but there'll locally be deviations from that depending on how you sampled it, or God knows what sort of like scientific method brought this data into HOT. But a picture like this has that problem. And the fact that as you move around a tiny little loop here, you're going to move a tiny angle, not some huge 1/6 of a rotation. So I wanted to propose a solution, sketch a solution to both of those problems, which is the same solution, which is a subdivider. A subdivider will be like an operation on polygons that takes a kgon to an n times kgon by adding n points between each pair of vertices. You do this in AGDA, I think. So now you've gone from, say, 5 to 5 times 6, or from 5 to 5 times 6 times 7. Take a least common multiple, 5 times 6 times 7, 210, and make them all 210-sided in your map T. So instead of the T I did, which was just link, compose that with something that adds a whole bunch of points. And it can vary from point to point. This number n can vary by the vertex you're at, so that everybody can come out to 210. So now they're all equal number of vertices, and then you can also do smaller angles. You might need to subdivide it, I don't know, even more to get tiny angles. And so something like that should let you do fine-grained. But I have not thought that all the way through. But the octahedron is definitely special, so there's more to do to move beyond that.
Okay. If there are no further questions, let's thank Greg again with one more round of silent applause.
Thank you.
I might not, Dan, you might have to stop the recording because